One limitation of prior work is that they all require good pose priors for training. In this figure, we can observe that with good pose distribution on the left three columns, 3D-aware models generate better results than given with poor pose distribution on the right three columns, which indicates the importance of pose priors. We can have access to ground truth poses for some types of data, but it is very hard to generalize to all types of data. Comparing is a method that tries to learn 3D-aware image synthesis without knowing an accurate pose distribution. But we found that it is also sensitive to the initialization of their pose distribution. Therefore, we would like to free the model from the requirements of pose priors. We propose a method called POV3D. In POV3D, we first redesign the generator to make it pose-free. In the conventional 3D-aware generator, the camera pose is sampled from a prior distribution. Now, we propose to learn poses from latent space, where we introduce a pose learner to infer the pose for rendering. Therefore, our generator aims at approximating the conditional probability only from the latent observation, which is prone to simulating the native data distribution without taking the pose prior into account. Only making the generator pose-free can possibly lead to wrong generation, because sometimes concave shapes can also be a not that perfect solution. Therefore, we propose the pose-aware discriminator. We assign a pose prediction task to it apart from the real-fake discrimination. For one thing, it learns pose prediction from the generator by taking the inferred pose from the latent space as a pseudo-label. For another, it predicts a camera pose from the given image and then use it as a pseudo-label for conditional real-fake discrimination. Here is the overview of our method. The generator uses a pose learner to infer a pose from the latent space. The pose learner gets supervision from the conditional real-fake discrimination in discriminator. In the pose-aware discriminator, the pose branch learns from the generator and will further predict the pose for conditional discrimination. With such a loop-back optimization process, two pose branches can align the fake data with the distribution of the dataset. However, only with these losses for training can result in planar shapes. Therefore, we introduce the symmetry loss to avoid this issue. For each inferred pose, we find the symmetry pose for it regarding the predefined plane. And we also calculate adversarial loss on the image rendered from the symmetry pose. Here are some qualitative results. Compared with pose-free method comparing, ours generate much better image as well as the geometry. And compared with EG3D, a method that have access to ground truth poses, our image quality and geometry quality are on par. For quantitative comparison, other than FID score, we follow EG3D to calculate depth error and pose error to evaluate the geometry quality and pose accuracy, where depths and poses are estimated from a pre-trained model and are used to calculate the difference with the inferred camera pose and the rendered depths. Besides, we also use Jensen-Shannon divergence to measure the similarity between the pose distribution of the dataset and the pose distribution inferred from the latent space. Here are the quantitative comparisons. Our approach significantly outperforms Campari and Campari plus EG3D in terms of depth error, pose error, and Jensen-Shannon divergence score. Our method also yields results on par with EG3D. In addition, We conduct ablation studies to verify the effectiveness of each component. We can see that without symmetry loss, the depth error increases, which means that the shape quality becomes worse. And without pose-aware discriminator, the generator synthesizes round shapes and results in large depth error. Learning rate of the pose learner in the generator also matters a lot. If the learning rate is too small or too large, the network will fail to synthesize high-quality 3D-aware images. Since our generator can infer pose from the latent space, we visualize the distribution it learns. The light blue denotes the pose distribution of the dataset, and dark blue represents the pose distribution of the generator. Our method well captures the pose distribution of the dataset. Note that there is a slight shift of elevation distribution on the FF2 dataset. The reason is that the model can automatically learn a canonical space for best performance during training, which may be different from the predefined one. We also visualize the pose distribution predicted by the discriminator on the dataset. Same as before, the light blue denotes the pose distribution of the dataset, and the dark blue represents the pose distribution predicted by the discriminator. The discriminator can capture the distribution similar to the dataset. In summary, pose is crucial for 3D-aware image synthesis. Bad pose priors can hurt the synthesis quality. By deriving poses from the latent space and making the discriminator pose-aware, we can enable 3D-aware image synthesis without pose priors. That's all. Thanks for listening.